Northrop Grumman Aerospace Systems, USA. We are indeed grateful to Dr. Sudhakar Rao for graciously and readily accept our invitation. Although he doesn't need any introduction, let me brief in his credential. Dr. Sudhakar Rao received B.Tech from NIT Warangal in 1974, M.Tech from IIT Kharagpur in 1976, and PhD in Electrical Engineering from IIT Madras in 1980. He worked at ECL Hyderabad and LRDE Bangalore and was the postdoctoral fellow at the University of Trondheim, Norway, and then as a research associate at University of Manitoba, Canada during 1981 and 83. Over the past 37 years, he worked at Spar Aerospace Limited, Boeing Satellite Systems, Lockheed Martin, and now at Northrop Grumman, and contributed to antenna and payloads for more than 80 different satellites. He authored over 210 technical papers and was awarded with 56 US and European patents and 5 trade secrets. He authored and co-edited 3 textbook volumes on Handbook of Reflector Antennas and Feed System that were published in June 2013 by the Arctic House. Dr. Rao is an IEEE Life Fellow and a Fellow of IET. He received several awards and recognition that include IEEE Benjamin Bracklin Key Award in 2006, Delaware Valley Engineer of the Year in 2008, and Asian American Engineer for the Year in 2018. IEEE Judith Resnick Technical Field Award in 2009 for pioneering work in aerospace engineering, IEEE Region 6 Outstanding Engineer Award for 2017, and the 2017 and 2020 Northrop Grumman President Award for Innovation and Contribution to Key Program. Dr. Rao served as the Distinguished Lecturer for the IEEE APS for a 3-year period. He was the founder and chair for the IEEE APS Industry Initiative Committee during 2011 and 2015. IEEE APS Fellow Evaluation Committee member during 2015 to 2017, Associate Editor of the IEEE Antennas and Propagation Magazine, Antenna Applications Corner, Associate Editor for the IEEE Transactions on Antennas and Propagation, and Associate Editor of IEEE AWPL. Recently, he was appointed by the IEEE Board of Directors to serve as the IEEE Fellow Committee member for 2020 and 2021. Now, I would like to hand over the session to Dr. Rao, and we are eagerly waiting for his interesting lecture. Sir, please, sir, go ahead. Now the stage is yours. Sir, now I will make you as a presenter, then you can able to share your PPT, sir.
Okay. Thanks, Professor Karthikeyan, for your kind introduction. So I want to thank Nrsinga Pradhan Chauhan, IEEE Trichy Student Branch Chair, for his persistence in making this happen. So IEEE needs a lot of young volunteers like you, Nrsinga. Thanks very much. Can you hear me?
Yeah, yes, sir.
Okay. My talk today is on antenna systems for satellites, aircrafts, and ground communications. Since registered participants are students, young professionals from industry and academia, I thought I'll give a brief introduction to satellite communications. And then a lot of people are interested in what I'm doing recently, so I'll present some of the work I've been doing for the past 5 months, which I think is relatively new and it has not been presented elsewhere. So first time you're hearing. So and then I'll come back to satellite communications. I'll show you some of the programs, how to design the antenna systems for satellite communication. Finally, I'll show some few videos are there. So they're self-explanatory. So probably a couple of minutes, maybe 1 or 2 minutes. So I'll show you so that you guys see how the satellite communication antennas or any other antennas are designed and used in practice. So if you have any questions, please type them, and then Professor Karthikeyan will coordinate at the end of the talk. And please make sure you mute your speakers so that everybody can hear. So should I share it, Professor Karthikeyan?
To share, sir. No problem. You can able to share.
Can you see my screen?
No, sir, not yet. Yeah, now it is visible, sir.
Okay. So good morning for all the people in USA and regions 1 to 6, and good afternoon for my friends and from Europe, and also good evening for all the people from India and Asia. So thanks for joining the talk. So what I want to do is go through. This is the agenda. So I want to give a brief introduction to satellite communication. So basically antennas or commercial satellites or commercial communication systems are very challenging and interesting. It's a very interesting and challenging field. So if you're an antenna engineer, I think you'll be excited to work on antennas because every design is different, so nothing repeats, unlike some of the back-end electronics or amplifiers. I think sometimes you have set of unique tubes or SSPAs, and it's whereas in antennas, I haven't seen any one design out of what I have worked over 45 years, and people working in the field also appreciate that. So plenty of scope for new developments and innovations. So if you're an young engineer, please do consider continuing in the antenna field. I think it's very exciting and a lot of shortage of antenna engineers, not just in USA, but across the world. So I'll go through brief antenna systems for communications, so satellite, ground antennas and aircraft antennas, show some examples quickly. Then give you introduction to satellite communication antennas. And then go through what are the basic antenna and system parameters to design these systems. And give some basics for reflector antennas. And then give you some basics for phased arrays. So people think these designs are very complicated, but I don't think so. If you understand the basics, they are very simple, and you can design 80% of the systems probably within a couple of days. You don't need to run any simulations. People spend a lot of time in RF simulations trying to perfect, and no, that's not how you design. So you cannot design by analysis. So you have to come with a good starting point and use the software tools to verify the design. So that way you can do the designs very quickly, which is important when you're working on proposals because you don't have that much time to produce the designs. So I'll show you some recent developments. These are mainly for the past 6 months. I've been working on the ground and vehicular antennas, aircrafts and missiles. So I'll show you some developments which are new. So this is the UAV, I think what you see. Northrop Grumman does a lot of UAVs and aircrafts and satellites. So these are some examples. Some conclusions at the end. So basically antennas are eyes and ears of satellite or aircraft or ground communication systems. So they're the key components of the payload. So design of these systems are very important, and we are upfront, and we are also on the back end where we test the whole payload through antennas. So these are some of the examples of antennas for day-to-day communications. You can see on the left, top left, satellite, which is advanced AEHF satellite built by Northrop Grumman. We launched about 6 satellites. So it's a global system. And on the right side top, you see the EVAX aircraft. You can see the phased array on the top, expand phased array. And on the bottom left, you can see the B-2 bomber aircraft, which is stealthy. So that was B-2. Currently, we have a contract to develop more advanced, more stealthy bomber aircraft, B-21. So that development started a couple of years back. So it's another 20-year program. So a lot of development in that area. The one in the middle is the ground station antenna, which is 1,000-foot diameter. is the world's, used to be the world's largest radio telescope, built in Puerto Rico, between the mountains. So this has about, it's 1,000-foot diameter, but the Chinese have built another one which is larger than this one. That is about 1,500-foot diameter. So this one is made out of 30,000 panels, aluminum panels. This goes from VHF to UHF. UHF is the main communication link, but other high frequency bands as well. The one on the right is basically deep space network, DSN, 64 meter by CSRO in Australia. So this is just to show the examples. So all these systems, antenna plays a key role in providing the communication links. If you are an antenna engineer, you cannot say that I design only work on satellites, work only on reflectors. So you should be able to adapt and work any given application. So it doesn't matter whether it's aircraft or even wireless communications or even cell phones. So I have to adapt to the requirements. So I think this is a small video to show you the
advanced EHF payload, part of a system delivering unprecedented levels of assured networked interconnectivity to rapidly deployable maritime, air, and ground forces, flexibly, where and when needed, immune from denial of service attacks, available in all levels of conflict. The payload puts the advanced in advanced EHF. A highly advanced digital processor serves as a switchboard in the sky, providing an order of magnitude increase in capacity versus Millstar, while supporting thousands of direct and rapidly reconfigurable flexible network connections between users on a variety of operational platforms. The processor implements advanced security and anti-jam waveform features to maintain both confidentiality and undeniable availability of U.S. international partner and coalition networks operating at multiple security levels and within separate security domains. As with Millstar, the advanced EHF payload supports user logon and communications at lower data rates, worldwide, anytime, without prior coordination, and in the most hostile environments imaginable. And like Millstar, the payload features highly sensitive receive equipment, capable of accurately processing lower power spread spectrum signals in EHF band, enabling low probability of detection, stealthy communications in support of special operations. The payload's fast-hopping uplink and downlink phased array antennas can flexibly cover a much wider area of the globe simultaneously with high-capacity service. While both Millstar 2 and Advanced EHF provide 6 1-degree spot beams which can be steered to anywhere in the satellite field of view via gimbal drive antennas, the Advanced EHF phased arrays support an additional 6 1-degree shareable spot beams, instantaneously steerable to any location within the satellite field of view. Operational planners have the option of allocating the capacity associated with each shareable beam among up to 4 separate regions within the satellite field of view, done on a hop-by-hop basis in milliseconds, transparent to individual users. Even with each payload's ability to deliver high-capacity coverage to upwards of 30 separate regions, there still could be a need to provide higher capacity service to isolated users outside of these regions. The advanced EHF.
Okay, you have seen the advanced EHF. So that one is actually a global satellite system. It has 6 satellites actually. I think some redundancy there. It's a geostationary orbit. So the key for that, as you heard, is the uplink phased array, which works at 45 gigahertz. So that basically provides communications even in the contested environment. So it has anti-jamming capability. So because it's a phased array, each has about, receive array has about 400 elements. So that can anti-jam up to multiple jammers actually. I cannot tell the actual number. And then other things, since they have to communicate each other, satellite to satellite, it has also inter-satellite links that those things operate at 60 gigahertz. So total, actually, if you see the antenna, it has about 16 antennas on the spacecraft. So probably most advanced satellite. So this is the introduction to satellite communication antennas. So what is a satellite? So it acts as a relay or link. So main objective is to connect the users on the ground, or connect users to the ground stations, or among the ground stations. So that's the main purpose. So this is done through either a geostationary orbit, or through LEO or MEO, low Earth orbit or medium Earth orbit satellites. What you can see on the top right-hand corner is a satellite located in the geostationary orbit, about 36,000 kilometers away above the Earth. So when it sees the Earth, it sees an angle of 17.4, so plus minus 8.7 degrees. So each degree covers about 630 kilometers on the ground, very large area. So that way you can provide very high gain performance, which is required. And then it basically, if you see the on the bottom right side, it shows the link, how the satellite communicates to the ground station antennas. If you see the right side, what you have is a ground station antenna, which it transmits, say, for example, C-band. It transmits 6 gigahertz, so satellite receives at 6 gigahertz. So down converts to 4 gigahertz and transmits back to the ground station. So one is called the uplink, other is called the downlink. When the satellite transmits, it's called the downlink. And then you also have another link, which is a TT&C, telemetry telecommand, because you have to send telemetry signals back to the ground. So which has a status of the satellite and many other things, how much power, whether it's getting heated up, or a lot of parameters regarding the health of the satellite, and also some communication as well. On the left side, you can see direct broadcast downlink. So this is mainly to provide high definition channels to mostly TV users. So there it's a transmit. Downlink is most important. So that has to provide the highest EIRP. So uplink is very simple. It could be done with a simple horn. So for a global system, you can see the intersatellite, satellite to satellite communication. So that's called ISL, intersatellite link. And then you can see some of the GPS satellite, which is in the MEO orbit, which is about 20,000 kilometers. And then there are a lot of LEO systems now, which are about 1,000 kilometers or less. So you can see some of the systems on the left side, which is AEHF satellite, which is about 12 meter mesh type reflectors, the very large reflectors, because this is a test band. So you need a lot of gain. And then on the bottom, it's a direct TV type satellite. So key considerations, why it is different satellite communication, because you're in a vacuum. So, and then the satellite gets very hot when the sun shines on the satellite, so it gets very hot. But when the sun is on the back of the satellite, it gets very cold. So thermal is very important. So when you design components or antennas for these systems like diplexers, OMT, polarizers, horns, reflectors, you have to make sure that not just the ambient temperature, so you have to optimize the performance over the temperature range, which goes from minus 40 degrees, 140 degrees to plus 180 degrees C. So that's a large temperature change. So key components which are sensitive to temperatures, we all know that filters, diplexers, they're very, so when you design these systems, design over the wide thermal range, not just the ambient. So the transmit, it has high power, sometimes kilowatts of power. So you have to make sure that the payload doesn't multipack. So you have to do some analysis, and by analysis, you have to show at least 6 to 9 dB margin. Nowadays, 9 dB becomes a standard. And then passive intermodulation, so I'll talk about it later. So that's also very important. ESD, electrostatic discharge, is very important. So something like dielectrics, etc., try to avoid using them. If you have to use, then you have to make sure that you basically dissipate the charges through some means, maybe through the body of the spacecraft. So cross-pole is very important because most of the communication satellites, they reuse the frequency to increase the capacity by 2 times through dual polarizations, either vertical or horizontal polarization, or sometimes you can use left-hand circular polarization and right-hand circular polarization. So when you use both polarizations, your cross-pole isolation is very important. And typical spec is about 33 dB, so you can see how stringent the cross-pole is. And then the bandwidth. The bandwidth is very important because the larger the bandwidth, I think the more capacity you get through the satellite. SNR is the signal to noise ratio, which is the quality of the communication link. So you can sort of simply express through this equation. EIRP, which is effective isotropic radiated power through downlink transmit antenna. G over T is the figure of merit of the receive antenna, gain to noise temperature ratio. 228.6 is the Boltzmann constant, which is in dBW per Kelvin per Hertz. So that's basically, or joules per Kelvin. So that relates the temperature, energy to temperature at particle level. SL is the large negative number. So that's a space attenuation, both ways, uplink and downlink. So that's hundreds of dBs because it's 4 pi r over lambda square. It can depends on the frequency. And 10 log BW is the bandwidth in Hertz. So EIRP you can split into gain of the transmit antenna and the power input to the antenna. And then G over T is the gain of the receive antenna and system noise temperature. So most of them are negative numbers. So PI is positive, of course, the power, but that's a small number. If it is 50 watts per channel, it's about 17 dB or so. But the gain of the transmit receive, I think that's you need to optimize properly given the coverage or beam width considerations. So sometimes even 0.2, 0.3 dB makes a big difference, either winning the contract or not winning the contract. So that's very important parameter. So people spend a lot of time in getting the extra 0.1 dB out of the antenna, so by properly designing it. And these are some of the currently what you have on the bottom left. I think you see the geostationary belt in 2001, which has about 1800 satellites, you can see. So they're separated by 2-degree orbital arc. And then at one orbital locations, you can see a lot of satellites. So they're different, say, C-band, KU band, KU band. Sometimes the redundancy also, so that if the satellite fails, they can bring the satellite which is parked there slightly higher altitude and then bring it back so that you don't disturb the communications. So that was in 2001, but now it is more than 3,000 satellites, 3,500, I believe, latest. So they expect another grow by 4 times in the next 10 years. So then what do you do? So how do you pack more densely? So that means you have to reduce the spacing between the orbital arc. Orbital arc of 2 degrees came because the ground antennas can distinguish satellites which are separated by 2 degrees in the geostationary orbit. So that's how it became. But a lot of congestion and there are efforts to reduce the 2 degrees to 1 degree or less than 1 degree. I'll talk about it later. So these are some of the, you have seen the advanced AEHF satellite, small video, GPS-3. So this is, everybody knows GPS-3 and uses GPS-3. So this is done at L-band, L1, L2, L3, sorry, L1, L2, and L5. So 3 bands. So one is for, it's both for commercial as well as military applications. So WGS is wideband global satellite. So I worked on it for almost 5 years at Boeing, from the proposal to architecting antennas. So you can see it has a phase arrays that expand, transmit, receive on the native panel. and 10 Ka-band antennas, 5 on one side, 5 on the other side, are deployed, and each antenna can be gimbaled over the globe, so that you can move the beams around. So this is, I think there are about 12 satellites that has been launched, and Air Force declared that it's the most successful program, so which is good. ACES satellite, I talked about it. EchoStar 10, this is the Lockheed Martin program. So this is for direct broadcast satellites. So you can see multiple apertures to provide the multiple beams. And also it has a national beam as well across the corners. So these are the satellite services. I won't go through all of them, but you can see the ones marked in blue. So they're the basic services we'll be using. Broadcast satellite service, this direct TV type, etc. Fixed satellite service, they're very important because they provide communications for a given geographical area like country, so US or India or any other country. Inter-satellite services, we talked about it. When you have a constellation of satellites, you need to communicate to get the global communication satellite to satellite. That's done at 60 gigahertz. Mobile satellite service, this is typically done at L-band and S-band low frequencies, provide for the mobile users. And then currently it's personal communication. Sometimes they call it high throughput satellite, HTS. So these are done at K and Ka band. So K band is downlink and Ka band is uplink. So this is done through multiple spot beams. I'll go through that later. On the right, you can see there are three components you need for a satellite to work. One is, of course, the satellite. Other is a ground terminal, and other is a launch vehicle. So the launch is done typically in 3 stages. So first stage, it takes a satellite to about 50 miles above the Earth. And then the second stage takes it to 100 miles and puts in the transfer orbit. So once you're in the transfer orbit, the apogee kick motor actually raises the altitude to any given altitude level by controlling through ACS. So this is how the whole thing works. And then on the top, you can see the top right, you can see the LEO, MEO, and the GEO satellite orbits, 3 typically. So LEO varies from anywhere from 400 kilometers to 1,000 kilometers. MEO goes up to 20,000 kilometers. And typically the geostationary orbit is around 36,000 kilometers. So antenna design depend. There's no one design, so it depends on what service you're using and what coverage you're designing the satellite to. Okay. So type of satellite. So there are high gain antennas. Typically, that's what is needed for to close the links. So they're about 30 dBi to 70 dBi gain, depending upon the size of the antenna you use. The reflector antennas frequently used, I would say about 90% is reflector antennas. Lens antennas are hardly used, or I won't recommend anyone to use lens antennas because it has problems in the past. Dielectric lenses, it has ESD issues, so it's very difficult to bleed the charges. So these charges accumulate over time, and then finally it breaks the material, and you cannot use the system antenna for the communication. Waveguide lenses, people try to use it, but they're narrow bandwidth, so and heavy as well. So my rule of thumb is don't use dielectrics in space. So it's only problem. It doesn't give any solutions. So array antennas occasionally used. So that's probably the remaining 10% is array antennas. So they're mainly used for military, and nowadays I think people are trying to use for communication. So only reason they're attractive is because they provide the flexibility. They can adapt the beams, you can change the shape of the beam, you can locate it in a different place all electronically, but it also comes with the disadvantages. So power added efficiency is about 25% at the best, whereas reflector antennas with the tubes, you can get about almost 60% efficiency nowadays. So that's a big reason. So you have to dissipate a lot of heat into the spacecraft body through heat pipes, etc. So a lot of complexity, but when it's needed, of course, it's a good thing to use. Medium gain antennas, they're about 15 dBi to 25 dBi. So typically they're provided through global coverage horns. So to cover the whole globe plus minus 8.7 degrees. Typical gains are about 20 dBi or so. Low gain antennas, they're also important. People sometimes neglect it, but if you're in the transfer orbit, that's the only communication link provided to the ground. So through TT&C. So they're biconical antennas or waveguides sometimes to keep it simple, and horn antennas are also used sometimes. So services we talked about, fixed satellite service, broadcast satellite service, mobile satellite service, inter-satellite link, and personal communication satellites. So all these antennas you can see on the top right corner, you can design independently, but then when you put together and the performance is totally different. So you design individual antennas first, and then also you have to make sure that you model the spacecraft body and take care of the coupling between the antennas, though they're different frequencies. Sometimes they spread out some harmonics into the other bands. So those things you have to, unless you do this spacecraft simulations and the antenna suit, I think you design, so it's not complete. So we have to do that before CDR for critical design review to the customer. So how antenna radiates? So this is one chart. I think you all know that to radiate you need time varying currents. So time varying currents produce electric fields. So the electric fields basically radiate E and H fields. So they're time harmonic electric and magnetic fields. So on the top left, you can see the signal generator, the transmission line, to propagate either waveguide or coaxial or any other media. Then you have a taper transition, which is very important. So this is the transition from bounded media to free space, how it radiates. So you have to match properly, and you have to design the antenna system. When I call it taper transition, it's basic antenna design, either a horn or reflector or phased array. So you have to match it to the free space, and you have to design antenna system to meet the requirements, either beamwidth or gain or any other constraints. So then you can see the electric fields, how they radiate into free space. So important part is basically the transmission line and the tapered part to free space. So that's basically the antenna. And you can see on the right side how it's a simple dipole. You can see how on the top how the currents are and how the fields are radiated. This we know a simple dipole radiation pattern, figure of 8. And then on the bottom you can see how the charges are accumulated. So these charges, moving charges, basically creates the fields, and the fields will radiate into free space. So these are the figure of merit, ERP and GOT, gain to noise temperature for the satellite. Effective isotropic radiated power is power transmitted through the antenna times the gain of the antenna. Of course, if it is a dB is just a plus sign. So this is generally expressed in dBW. So idea here is basically if you see the top right, this power through high power amplifiers, say TWTA. So then you have cables, filters, or waveguides, etc. There's some losses there. So this is the losses you have to minimize, and then the gain of the antenna. So basically PT is the power input to the antenna, including the losses. G over T is gain to noise temperature ratio. So this is the figure of merit of the receive system or the uplink system. So G is gain of the antenna. Receive antenna, sometimes transmit receive antennas are different, so the gains could be different. So T is the system noise temperature. So you can see how system noise temperature is calculated. It has some losses, noise figure of the LNA. So you need to take those two, and also temperature of the antenna. Depending on the satellite where it is, the antenna noise temperature changes. So you have to basically integrate the radiation patterns with the proper noise temperature. So ground is hot and cold sky is typically 290 degrees, and sky is about 5 degrees. So when you integrate, I think it comes less than 290 degrees, depending on the satellite. So antenna gain is actually a very complicated parameter, depends on the design of the satellite system, coverage, a lot of other things, size of the antenna, etc. So it plays a key role both in ERP and GOT. So these are some basics about radiation from apertures. So I think the theory is important because you have to know if you have a square aperture uniformly illuminated, we know it's a sin X over X patterns. So you can see how the patterns, you can actually, using a calculator, you can see what is the beam which you get. Sometimes you need to do that. And circular aperture, you know, it's a normalized radiation pattern is 2J1X over X. Bessel functions of the first kind, J1X. X is Ka sine theta. So side lobes, you can see the square aperture that it has 13.2 dB side lobes. Circular aperture has 17.7 dB side lobe. So sometimes when you design the phase arrays, so it's important to reduce the side lobe level. So most of the cases you see circular apertures or hexagonal apertures. So on the right side, you can see the practical patterns, how they look. They don't look like either of them on the left side. So when you design the practical antennas, so on the top right is radiation patterns of the corrugated horn. So and then nowadays, I think we don't use corrugated horns. We basically use smooth wall horns to reduce the mass, and you get actually almost the same performance. Actually, much better in terms of efficiency. So some quick basics on the reflector antennas. So it has basically two components: reflector assembly and feed assembly. Both are complicated. So reflector assembly provides a required gain. So based on the gain requirement, you design the size of the reflector, which is pretty easy. It determines the coverage, shape, scan loss, sometimes beam squint. So it's a reflector. Sometimes you have to thermally treat the reflectors either through paint or some cover. Deployment, boom and mechanisms. If it is large reflectors, you have to deploy them. So to put on the side of the spacecraft. And then sometimes you have to put gimbal systems so to move the reflector so that you can scan the beam to different directions. So what are important is surface accuracy, loss. What is the loss through when you paint the reflector? It has certain losses, so you want to minimize them. And the mass, of course, sometimes if it is big reflectors, you use mesh reflector. Otherwise, you typically use graphite reflectors. You don't use aluminum reflectors. People try to use aluminum with vacuum deposited aluminum paint, but problems there with VDA, and it's expensive as well. Composite graphite reflectors are very stable, and those are typically used. So feed assembly is not just the horn. So it has OMT or the mode transducer. It has a polarizer, sometimes to generate circular polarization. It has filters, diplexers to separate the TX-RX bands and also filter out unwanted frequencies. So it also has test couplers. So sometimes you have to do the payload testing through test couplers instead of going through the reflectors, etc. During the TVAC, reflectors are not deployed, so you have to go through the feed array. So that's when test couplers are used for system level testing. Waveguide interfaces to repeater. So waveguides typically we use because low loss. So you need to somehow connect the output of the horn, for example, to the repeater. So it has some fixed waveguides and some flexible waveguides so that you don't put too much tension on the joints. So it also provides proper illumination on the reflector. So it dictates the bandwidth. So if you want wideband, so you have to design, or if you want a diplex feed, which can use both for transmit and receive, so the bandwidth becomes very large, 60 to 70%. So you have to design the feed horns and feed components to meet those bandwidths. Polarization. Cross-pol is very important. Again, we are looking for when you design these feeds, I normally try to design at least 40 dB cross-pole isolation, so that you can meet the overall 33 dB cross-pole isolation for the antenna. So filtering is important, and insertion loss, you want to minimize the insertion loss, because if it is a transmit antenna, so insertion loss means if it is 1 dB insertion loss, you lose almost 20% of the power. So that's very important. The power handling is important, so you have to make sure all components are designed to handle the power. So you have to do some analysis. Thermal is important, and low PIM, passive intermodulation, is important, because if you use the same antenna for transmit receive, which is a trend now to minimize the cost. So transmit, there are multi-channels, so they beat against each other and create intermodes. So if these intermodes fall in the sensitive receivers, so they blow up the LNAs. So you have to minimize those intermodulation products. So these are some basic reflector antenna types. So what you see is a single reflector, center fed. So then you have offset fed reflectors. So typically we use mostly offset fed reflectors, because you don't have any blockage either through the feed or sub-reflector if you have. So we'll try to use an offset configuration. Then you have a standard Cassegrain system where your sub-reflector is advantage with the dual reflector system is feed is very close to the reflector, so you minimize the losses, and then you don't need any cable runs coming from a single reflector. So sub-reflector typically, sometimes it's a shaped, so it's a convex sub-reflector. Gregorian is when you use the ellipsoid as a sub-reflector, so it is a concave type sub-reflector. So these are very easy to design and get the performance pretty close to what you want. So gain is basically 4 pi over lambda square times the efficiency. So you can see the efficiency can split into spillover efficiency, efficiency due to cross-pole, efficiency due to aperture illumination, etc. So these some basics on the reflector antennas. Since we use mostly single offset reflectors, I showed a single reflector geometry where you can see the reflector, which is, and then it has certain focal length. Typically, F over D determines the scan performance of the system, and you have multiple feeds. So you prefer to have a large F over D. So typically it ranges from 0.8 to 1.5 or so, depending on the application. So then your θ1 is the half subtended angle on the subreflector. So that basically determines the illumination taper. So you can get directivity very easily, 10 log of 10, 4 pi over lambda square. So eta f is the efficiency, which has, you can see below, it depends on the geometry, θ1 and n. N is the, because you have a feed at the focal point, so it is eliminating plus minus θ1 angle on the reflector edges. So you can determine n very easily through taper required on the reflector. So typically we use about 15 dB taper. So 12 dB to 15 dB, but I prefer to use about 15 dB taper on the reflector for other reasons. So once you determine n, you can easily calculate. So it basically depends on the efficiency and which depends on the feed taper. You can see some of these equations and how you can quickly design the antenna system without doing any analysis. I showed you the efficiency before. So this is for one case where horn wavelength, horn size. So if you use about one wavelength, then you can see the efficiency, which is on the left side. So that's about 40, 46, 40, 48 dB, 48%. The other curves are beam overlap if you have multiple beams, and then the side lobe levels on the right side. So, but if you use something like 2.2 lambda, then you can see the efficiency hitting almost 80%. So that's probably optimum. And then on the right side, you can see top right how the taper affects the efficiency. So typically around 12 dB it peaks, so 10 to 12 dB. So that's what people use, but some cases I think you need more taper. So if you are using the same horn for transmit receive, uplink downlink, at least on the transmit side, you want to have 15 dB taper. So receive, sometimes it could go to 20 dB taper. So these are some of the configurations of the antenna. You can see the multiple beam antennas. You can see the set on the top left. You can see the satellite body. So you see the solar panels, north-south directions, they're deployed. So depending on the how much power, DC power you have to use more panels to support the power. And then you see a lot of reflectors deployed, 2 on the left side, the east side, 2 on the west side, and then some reflector on the nadir panel, and some TT&C and the global horns. So this is typical payload, how it is in the deployed configuration. And in the middle top, you see how it is a stowed configuration before you launch, because everything has to fit within 3 to 4 meter diameter of the launch vehicle. So it means all these reflectors have to be deployed together, stowed together. And then some of the patterns you see, I think, on the coverages, different frequency bands, C-band and Ka band on the top. And on the bottom left, you can see the DBS type satellite, direct broadcast satellite, where downlink is important. So this is a Ku band, so you have to make sure that you provide more gain on the regions where it rains a lot. Like this is a CONUS, continental United States. So Florida, it rains a lot, and East Coast also it rains, so you provide more gain there. And in the Midwest and Western regions, it hardly not the complete West regions like Seattle, etc. But New Mexico and Southern California, it doesn't rain, so you don't need that much gain. So basically, you take gain from one area and give it to the other area where it's needed. So this one covers both Alaska and Hawaii as well. So one antenna can provide all this. So the way you do this is by shaping the reflector surface. So this is called weighted coverage design. So you can see the bicone antenna for TT&C, command on the top and telemetry on the bottom. So these are the slots to provide uniform coverage in the annular regions, and some feed systems. So again, the challenges are thermal, high power, PIM, ESD, cross-pole bandwidth. So in the designs, early designs, we have to take care of all this. Otherwise, you'll end up in very costly fixes. So I think it all depends on how you design the initial system. So some fundamentals on the phased arrays. So phased arrays, we all know that it has a number of elements. Say on the receive side, you have LNAs, phase shifters, attenuators, and then down converters and so what is important here, I think requirements wise, it's a bandwidth is important, scan coverage is important, how far you're scanning from the both side, polarization is important, and the gain is important. So grids, I think how you design square grid or hex grid. So typically there are only 2 types. So people try to use other types like sparse array and other things, but if you have a wide scan application, so those things won't work together. And also there gets complex because the spacing changes. So when you go on the back end, amplifiers, etc., you have different spacing, so it becomes packaging becomes a bit complexity. So I try to keep only design all these phase arrays either with square grid or hex grid. So nothing fancy. Element spacing depends on the maximum scan angle. So you can calculate the equation very easily. So theta g is the grading lobe. So you want to keep the grading lobes outside the coverage. So for a geostationary satellite, you have plus minus 8.7 max the coverage. So you try to put the grading lobes around 12 degrees or 13 degrees. So actually you want the grading lobes. You don't want to really suppress the grading lobes completely, because if you want to suppress completely, which is not required, then your element spacing becomes so small and you need more elements. So number of elements exponentially increases with the spacing. So definitely you want to minimize the complexity and go with grading lobes. You design the system with grading lobes. And theta s is the scan angle. So, and always design, when you design the grading lobes, do it highest frequency of the band. And element directivity depends on the grid you have. So basically it's area of the grid times efficiency, either a square grid or hexagonal grid. And when you evaluate the directivity, you evaluate the lowest frequency, because that's the lowest directivity of the gain. Scan loss, of course, scan loss is dictated mainly by the element patterns. So element roll-off. So it's given by, you have the equation here, scan loss equation. So you can actually use the paper which we published with one of the interns I had. He worked for 2 years with me. I think he's one of the most brilliant guys I worked with. So he actually programmed all the equations, make the software to sort of design these systems. So it was published in April 2020. So you can use that to see how to design principles and guidelines of phase arrays as well as reflector antennas. It's a good starting point, and for people who wants to understand. So all these systems, they have to have some mismatch, and will have some mismatch. So sometimes you etch on a dielectric for other applications, not the space. So you need to take the dielectric losses, insertion loss. And then these complex systems, you don't design without any implementation margin. So I typically use half a dB implementation margin and half a dB front-end losses. So typically 1 dB loss. So number of elements required is very easy. So you can calculate n required, 10 to the power 0.1. GM is the minimum gain required. Then add 1 dB for these front-end losses and implementation loss. And then you add the scan loss, and then take away the directivity of the element. So directivity of the element is depends on the grid area. And then I think you want to keep an integer value if you want to design a square aperture or something. If it is a hexagonal, it doesn't matter. So you can see some trends here on the bottom left. So for minimum array gain, depending on the maximum scan, say both side is to get the particular gain, you need only about 100 elements. But if you go to 70-degree scan, you need almost more than 3,000, 4,000 elements. So because we have 7 to 8 dB scan loss, so you need to compensate that and increase the number of elements. So also it's, you see the phase array here. This is advanced AEHF receive phase array. So you can see the 400 elements horns. They're basically typically about 3 lambda type diameter. So you have a thermal cover to minimize the temperature excursions for the receivers. And then the heat pipes, heat generated by LNAs and back-end electronics, say down converters. So you need to heat pipes you have to dump into spacecraft panels. Heat pipes are important. And this is done digitally, so there's a digital processor. So I'll talk about some recent developments, because a lot of people from the industry joined. So I thought maybe I'll show some. These are the developments I have been working with the past 5 months, 5 to 6 months this year. So this is a compact antenna technology for protected forward communications. So this is for the ground, mainly for the soldiers on the ground, how they communicate with harsh environments, and they have aircrafts, enemy aircrafts flying over, and how they communicate with local areas, how they communicate with headquarters, and how they communicate with aircrafts, and also how they communicate with satellites. So The soldier will be carrying the manpack, so all these antennas have to be either on the manpack. These are all called radios. They're different frequencies. So starting from L band, I think there are a lot of radio systems. EHF as well, and K band, KU band, and KA band as well. KA band is basically to communicate with the WGS satellite, so at 20 and 30 gigahertz. So K band is for COM1 local communications. So that it has both the transmit receive, and then it has also omni antennas which are mounted on at Ka band on the backpack. So I'll show you that. So this is the air and ground communication. So at K band, for example, this is one frequency band I'll show. This is communication on the move. So when the soldier is moving in the battlefield area. So it has pen cap. We developed a thing called pen cap for air communications for aircrafts as well, and also bunker antenna. We call it bunker because the shape of the antenna looks like it's a bunker shape. So we call it bunker antenna. They're all omni antennas. Some they provide 2 pi radians coverage, so you need the 2 antennas on the aircrafts, especially UAVs. Bunker antenna need to cover all 4 pi radians because you cannot lose the communication. So these are low data rates. And then you have communication at the halt. So when the soldier is lying down or when he has some time, so he can work through the phase arrays, 10 by 10 phase array. So that's also on the backpack. And some, I think, Ka band, I think they're separate phase array systems which are mounted on a tripod and can easily be assembled and disassembled. So key for these programs is actually the mass is very important because soldier cannot carry too much mass, and DC power and dissipation is very important because otherwise it gets too hot, and then it has to be cheap, so and lightweight as well. So this is the pen cap antenna for UAVs. You can see the UAV Predator, Northrop Grumman's one of the designs. So actually placed, this is 2 antennas. Actually, they started when we are designing for manpack. So customer is interested. They like this and they like this design and said, can you modify this for UAVs and aircraft? So that's what we did. So you need 2 of them, one probably on the bottom of the wing and on the other one on the top of the wing. Since they are very tiny, you can see the size here. 0.6 by 1.2 inch diameter, and the ground plane you can see on the top. Actually, other feature is it has to withstand a harsh environment, sometimes sand, sometimes rain, water, dust, etc. So we have the blue cover is basically radar, and then you can see the antenna. It's a simple antenna, not too complicated, but everything put together is you have to make it mechanically sturdy and strong. So basic antenna is a CP, circular polarization, right-hand polarization. So it's a single feed. So it's a circular patch with etched corners, 45 degrees to generate CP. So we made these. You can see the antenna which is made on the bottom, antenna by itself, and the radome cover on the top. And it's important that you design properly because you don't want too many iterations. So actually we got our designs correctly, and we measured the patterns, everything, and it's the right on. So if you design properly, I think sometimes you don't need to even measure. So whereas since this is first one, I think we have to do the measurements. So the dielectric constant of the material varies. So customer gave the range, so we designed for evaluated the 2 solid lines we can see are simulations with a different dielectric constant. One is 3.66, the blue dark line, and then the red dark line is 3.55, and then these are the 4 samples we made. So all of them actually more or less matches with some because of the tolerances, etc. So I think on the top left is the reflection coefficient, And the top right is basically the gain of the antenna, 4 different units and simulated gain. So as you know, the measurement of omnis is the most difficult thing. So high gain antennas you can measure very easily and it's no brainer. But when you go to the low gain and omni antennas over 4 pi iridians, that's the most difficult measurements. So we have to take a lot of precautions to do the accurate measurements as well. These are the patterns, measured patterns. You can see measured patterns are replayed because of the range, but we took a lot of precautions to minimize the ripples. And the solid line is basically the simulations. Solid line is the simulations, and the four are the measured data, so they more or less match. So this is the front side. So at different phi angles, 0, 90, 45, at 2 different frequencies, our band is 20.2 to 20.5. Sorry, 20.2 to 21.5. The actual frequency band is 21.2 to 21.5. We designed over a wider frequency. So this is the bunker antenna. So this is what is mounted on the band pack. So we call it bunker because it's, you can see this is all metal on the left bottom. So that's a geometry. So this is all 3D printed. So to make it cheap. And then it has a radome. You can see the blue cover on the top right. So that's basically the radome. You can see the SMA connector in the bottom. And then there's the radome has to be attached to the metal. So there's a glue actually. You need to use it, which is shown as a dark blue. Then you can see our spec. Actually, we meet our spec is about 95%, and we meet very easily. We have 2 different specs, but actual spec that matters is minus 9.2 dB ISP. That has to be met over 90% actually, not 95. We met very easily. And then on the right, you can see how wideband it is. So customer asked us to see the wideband performance. Since it's inverted F, we all know that it's wideband. So it actually goes from almost 12 dB, about 5 dB return loss, almost about 30 dB, 30 gigahertz, 12 gigahertz to 30 gigahertz. So you can see our bandwidth is very narrow in the blue box. So we get better than 18 dB return loss. And the complexity with this is the 2 modes here. One's the soldier is standing, other is soldier is sitting. So we have to deploy the antenna. So that's a tricky part. And then the mass is less than 250 grams. Actually, we made it much less than that, about 130 grams or so. You can see when the soldier is standing, which is the bottom picture. So you deploy the bunker antenna. So actual antenna you can see on the left-hand side with the blue. So that's basically inverted F. Then you need to have a rod, which is a support rod. And then you need to have a sleeve. So sleeve actually moves between the 2 stops, which are the blue left and right. And then there is a clip. So, and then there is on the right side, you can see the RF interface, which is SMA. Then when you're lying down in the battlefield, so you need to fold it so that it comes fold it so that the overall length goes from 25 inch to 13 inches. And then the clip is made of 3D material, 3D plastic. So you just remove the clip, and then I have some video to show how it deploys. So this is the antenna made. Again, this is the first time success. We designed properly. We made sure precautions in the design, and then we measured. I think we got almost what we want. So this is the setup in the range. So I think I have a video probably here to show you the deployment, how it's very easy for the soldier to take and then remove the clip and then slide the handle. So then when you want to put it back, when you're lying down, you can just do that. So that's very simple. You can see the antenna on the bottom here. So this is in the range. So range is also not easy to measure because you have the effect of the support rods, which are made of rexolite and very thin so that it doesn't scatter that much. And then you have a conduit, which basically provides the flexibility when you fold. So this is the nylon conduit. And the interface between the conduit and the support rod, you have to seal it so that nothing goes in. So like, for example, sand or in the battlefield, you don't know, rain or dust or particles. So that's the sealing is important. So we measured that in the range and show you some patterns. So here are the patterns measured versus computed. You can see the solid red is computed, and these are the measured for different, I think there's 6 units we measured. They're almost on top of each other, except I think one has slightly more ripples. But overall, I think it met all the requirements. Our gain spec is around -10 or -9.2, so which is about 90%. So we met that. Okay, next comes phase array. So these are, we need the phase arrays 10 by 10 actually for the Ka band communication at the halt. So to provide medium data rate signals. We try to use about 10 by 10 is about 100 elements, case 1. So problem is number of interfaces to the down converters and DFN is very large. So that makes it expensive. So then we tried to initially combine 4 to 1. We know that it won't work, but we wanted to see what it does. It's very simple. It's a passive combiner, and then phase shifters and attenuators for each subarray. So it's a 2 by 2 subarray. So you have only from 100 interfaces, you come down to 25 interfaces, which is good. But then the patterns are not that good. So case 3 is the selected configuration. So you still use the subarrays, but you have phase shifters and attenuators behind each subarray, behind each element as well as behind the subarray. So again, number of interfaces goes down to 25. So all this, we have done about 30 different cases to optimize the design. All are done within a couple of days using simple equations. So it's not, no computations at all. This is the 3 cases when the beam is scanned to 60 degrees. I think you can see case 1 and case 3, they're sitting on top of each other. On the bottom, on the top left-hand side, around 60 degrees, you can see they match very well. But if you go to case 2, where you have subarray without phase shifters, so the gain drops quite a bit, and also you have grading lobes coming up around 10 degrees or so, plus 10 degrees. So that's not good. And these are subarray element patterns, which are broad, and subarray patterns are narrow. Then the actual patterns of the whole array, 10 by 10 array. So for different amplitude distribution, sometimes we have to lower the side lobes when you're in a hostile environment where enemy aircrafts are flying over. So you need to communicate with the headquarters. So that you do through adapting the patterns as well as reducing the side lobe level. And this is the final design of the 10 by 10 array. So it scans, provides very large scan, plus minus 70, plus minus 80 degrees, so almost limit of any phased array. And we have to make it cheaper. So what we did is, of course, we don't want to go through around each element conventional ways to have via holes around grounded vias around each element, so that we basically create a cage so that surface wave won't propagate. But that becomes very expensive. So we don't want to do that, keep the design very simple. So we have one extra ring of elements. So they're match terminated, shown in the green. So instead of 10 by 10, we make it 12 by 12, and then load the outer ring with resistive materials. So then each element behaves very, very close to on-axis element. So square patch with the truncated corners is used to generate CP with a single feed point. We don't want to use VPHP and then combine with a coupler, so that also becomes expensive. So the cost is very important. So these are the computed patterns at different scans. 0, you can see at 80 degrees. Of course, the gain drops quite a bit. That's because of the element pattern roll off. You can't avoid that, but that's fine. It meets our requirement. And this is the Ka band which communicates with the WGS satellite. So here, because WGS operates both circular polarizations, LCP, RCP. So here the requirement is switchable polarization. So you can provide two phased arrays with switches, but then it's also expensive. So we don't want to do that. So what we did is a Madeleine polarizer. We make it like a square, put on top of the array. And then if you meet the tolerances, then what you can do is you just rotate it 90 degrees. So one is RHCP, other is LHCP. So it's very easy. So that's the design. And then when you interface the element ports to the IC ports, so IC ports are very small, so you have to use an interposer. So to bring the widely spaced element to smaller spacing of the IC. So this is done through another layer, call it interposer. So that's very easy. So this is another one I think I've been doing. How much time I have, Professor Karthikeyan?
Sir, you have another 10 minutes, sir.
Another?
Another 10 minutes we can have.
Okay, I'll try to finish it, but give me another 5 more minutes.
Yes, sir.
In case.
Yeah, okay, no problem.
So this is the vehicular antennas. This we started actually a couple of years back, but then one of the subcontractor could not meet the specs, so they asked me to look into, and this is one of the biggest programs we got for ground-based strategic deterrent program called GBSD. So you can see the Minuteman missile here. So you need to communicate when the missile is launched through L band as well as GPS bands L1, L2, and also TT&C bands at S band. So you need to provide a continuous communication, though it is only a couple of minutes, but still it's very important to track the missiles and redirect it if needed. So L1 is, we all know, 1.57 around, and L2 is about 1.2 in the S band. So key thing for this is initially the vendor was doing a 2-element patch. So they put the 2 elements 180 degrees away on the circumference of the missile. You can see on the right hand side. So the red curve basically shows the deep nulls, because when you have 0 and 180 degrees combined together, so we all know that their interference patterns will be at 90 degrees, plus minus 90 degrees. You can see deep nulls because they're interfering each other. So we sort of modified that initially to make it simple and cheaper through only 2 elements, but they're oppositely polarized. They're LP linearly polarized. One is vertical, other is horizontal. So when you go at 90 degrees, actually your interference is gone. So yeah, because the cross-pole isolation you get. So you can see the blue curve. So of course the gain drops, but we still made the spec, but phase variation is very important because we have a spec of, for that case, 20 degrees per degree maximum phase variation. We made that with a big margin, but then actually they want to use advanced coding. So then it, from 20 degrees per degree, they reduced to 2 degrees per degree. So then we have to go with a new design. So this is the 2-element prototype. Actually, we simulated, we measured. You can see the patterns on the top, azimuth cut patterns, radiation patterns, amplitude, and phase patterns. So they match very well, reasonable accuracy. So that gave us a confidence in the measurement systems and the simulations. So we went with a novel sector antenna. So instead of 2 elements, of course, you have to increase the number of elements to make the phase very stable, to almost 10 times more stringent than before. So this is called a sector antenna. We basically have 6 sectors. So each sector has actually one of the designs have actually a BFN here, so which is about 1 dB more loss. So the design here actually there's no BFN. So basically you input one and actually excite the 5 slots, and then no power is left at the end. And if there is power, we can put a load there to absorb the power. It's more like a traveling wave approach. So advantage is you minimize the ripples, both amplitude and phase. At the same time, improve the losses by a dB. So, and also advantage is there's no dielectric. Before, I think they were doing patches. So patches are heavy, and also ESD issues because the temperature goes more than 1000 degrees when it's launched. So some problems will be there. So here we don't want to do that. No dielectric at all. So it's actually a rigid waveguide, very thin waveguide. You can see one input and it radiates. So there's 6 sectors. So 6 sectors are combined through a coupler, 61 coupler. So that's it. Is a design. Of course, we have diplexes and other things. So this is for one frequency band, L1. Actually, now we are combining L1 and L2 within the same to reduce the height of the height of the antenna on the missile. And then actually we are combining the S-band also as part of it. There's another S-band ring which goes, so that is under development. You can see how it looks like around the vehicle. So this is another one which we recently did 1 gigahertz to 60 gigahertz antenna they wanted. So this is for a lot of applications for this 2.5G, 3G, 4G, 5G, and now they want to go to 6G. So this covers all those frequency bands, all those communication requirements for the GSM, wedge, and WCDMA waveforms. Actually, it supports. So we all know that 1 to 60 gigahertz, there is no antenna exists. So typically people, what they do is they do with Vivaldi's. So they're about 10 to 1 bandwidth ratio, or at the most 20 to 1 bandwidth ratio. They cannot support 60 to 1 bandwidth ratio. And they're expensive because to meet 43 dB gain, you need about 10,000 elements. So that's not even a starter. So what we did here is and also cost is very important. Again, this has to be carried by the soldier. So the mass spec they gave is about 50 pounds. So we made it 45 pounds. And also it has a gimbal system mounted on a tripod. So everything has to be gimbaled. So it's a low cost gimbal, which is about something like about 20K or so. So whole antenna actually, so you can see that it's segmented into 3 bands. High band is 20 to 60 gigahertz. So medium band is 8 gigahertz to 20 gigahertz. So high band is provided by a 12-foot ADE type reflector. Cheap, actually it's all aluminum, so no composite reflectors. MBA is provided through high efficiency horn, and LBA is the low band antenna, which is 1 gigahertz to 8. It is provided through COTS items, which is rigid horns with remote balls. These are standard items available from Pasternak. So you can see on the right side how the top right, how the directivity versus frequency plot, and then different frequencies, plots of HBA, MBA, and LBA. So all this work is done within probably maybe 3 weeks or so. And the gimbal is a procured item. It's a low-cost gimbal, and then it has to be mounted on a tripod. Everything is about 45 pounds. So cost of such system is instead of probably $6 or $7 million, it became like 250K. So reduced quite a bit. I think we're customer is happy, and hopefully we'll start this program soon. Other one I recently working was advanced ground antennas. So AFRL has a lot of ground antennas, almost about 200 of them at different locations, vary from 2.5 meters to 13 meters. So typically they provide the Ka band and the L and S band. So you can see on the left-hand side a 2.5 meter reflector with the L and S band feed at the top, and then the cable running through, and then Ka band horn at the border, feeding a subreflector. So subreflector is a frequency selective surface. which basically transmits the low band L and S band and reflects the Ka band. Oh, sorry, this is 5.4 meter antenna. So we have 2.5 meter design as well. So now they want to include other bands like X band, K band, lower Ka and upper Ka. So there are a lot of, so how you do that? And then we want to make it cheaper too. So we basically reuse the reflectors and then we remove the feeds on the top. We remove the struts, 4 struts actually coming to support the subreflector because we don't need the subreflector. We don't need the FSS. So subreflector is simple. So it's basic subreflector supported by the feed. The complexity is everything is in the feed. So how you sort of develop the feed. So it's basically a multi-coaxial feed system, nested coaxial feed system. So when you do that, actually not only provides the additional frequency bands, but also it improves the gain of the current existing bands at LS and Ka band by 1 dB because you don't have the strut blockage, you don't have the long cables, you don't have the loss of FSS. So I think we are currently building 3 prototypes to end of the year to give to the customer to implement. So after that, I think we need to build other ones as well. So here is the nested multi-coaxial feed array. It looks complicated, but a lot of hardware. I think you have to design it properly. So basically 3 apertures. So one goes from aperture 1 goes the high frequency band. It supports mostly Ka, and aperture 2 is the mid one, which basically supports X band and Ku band. And aperture 3 is basically supports low frequency bands, which is on the outer side of the nested coax. And then of course you need duplexers, you need the hybrids, you need the junctions, etc. So you have to design them properly. And then some cases you need switches to switch right hand to left hand polarizations. And then high frequency band has also tracking, so it complicates a bit, but it could be done. So this is the basic block diagram and how the patterns at different frequencies are computed patterns. Then this is the Whiskey T satellite. I told you before there's a congestion in the geostationary arc. So now actually this is high frequency, W V band. So V band is 71 to 76 gigahertz, which is transmit or downlink. And then W band is 81 to 86 gigahertz, which is the uplink or receive band. So this one provides about 5 gigahertz of bandwidth. So very useful for high capacity satellites, but no one knows what is the attenuation at these frequencies. So we build a pre-satellite for this called Whiskey. So that is, we build the payload is actually, it's going to be launched. So we have 5 ground sites at different AFR locations across corners. Some are in the rainy areas, some are dry areas. So we'll be measuring for next 3 to 4 years continuously signal attenuation as well as the depolarization effects. So that gives us how much attenuation is there in the atmosphere at these frequency bands. And then this is the next generation satellite. So we build the whole payload, W and V band. So antenna is simple. It's about 36-inch ADE type reflector, composite reflector. And then subreflector is metal and then fed with a feed. ADE design actually displays ellipsoid, so you don't have any blockage. So you get very high efficiency and high gain. So these are the frequencies, and this is the performance, and the complexity is in the feed. So you can see the feed horn illuminates the subreflector. Then you have septum polarizer. Since it's only one polarization, we terminate the other pole with the load. And then you have diplexer, so separating the transmit and receive frequencies. And each path has a test coupler to be able to test during the for the system testing during the integration. So this is, we just started this about a couple of months back. So this is the large deployable reflectors, Astromesh, that's Northrop Grumman. We make, this is an example of 12 meter. How it looks like mesh reflector, it's very lightweight. The mesh is made out of gold moly. about 1 mil in diameter, gold plated, high tensile strength, and it can withstand very extreme temperatures. Two designs. Harris also has another design, which is a hook column truss type. So we have front mesh and back mesh separated, supported by tension ties and the truss columns, whereas Harris has they don't have the back net, but they have a truss type structure supporting the front. Both are very good. So you can see the close view of the mesh. And typically we use 10 openings per inch at low frequencies, but if you go to high frequencies, you need about 30 to 40 openings per inch. So just another video, I think probably last video. This shows the NASA's SMAP, where we provided the reflector and NASA developed the payload. The complexities on the reflector, you can see once it's after 2 weeks, so solar panels are deployed. You can see the mechanical boom structure which carries the mesh reflector, which is in the black cylinder. So the feed is there actually, corrugated feed. So you can see the deployment starts. So this is a low Earth orbit about 650 kilometers above Earth. The main purpose of the satellite is to detect the soil moisture and the depletion of the icebergs in the polar areas, southern hemisphere. So the reflector rotates in about 35 degrees angle, conical angle. So it creates a conical swath on the Earth, and as the satellite moves, and then the spacecraft has to move in opposite directions to maintain the balance. And it rotates at about 15 RPM. The reflector, what I showed, is built by Northrop Grumman, 6-meter mesh reflector. You can see the swath as the satellite moves across. Yeah, probably because of the time, I'll leave it. So some multiple beam antennas, why we need multiple beam antennas versus contoured beam, because you get, instead of one beam covering the corners, you sort of have a frequency reuse and 60 beams. So alternate beams reuse the same frequency. So the bandwidth is split into 4 subbands and support one subband supports 1, 3, 5 alternate beams, and 2, 4, 6, etc. Then 10, 12, 14, then 11, 13, etc. So basically you have smaller beam, so your gain is high, almost 15 dB. So the link will have about 30 dB more gain. And spectral reuse, because you're reusing the same frequency 15 times. So reuse factor is about 15. So instead of say 1 gigahertz band, you have 15 gigahertz band. So that increases the capacity. So this basic concept. So not only that, since your gain is high, you can actually reduce the ground terminals too. So this is the MBA for local channel broadcast. Probably this is the most difficult design, because here you have to cover the market local channels based on cities. Like New York is number 1, Los Angeles is number 2, etc. based on the markets. And East Coast, you have to compensate for the rain, so you use smaller beams to cover multiple designated market areas. There are 216 of them in the US. So you cover actually multiple DMAs with one beam. So whereas West Coast or Midwest, the beams are very broad, so that's not a problem. So you don't need that much gain. So problem with that is the beams not only are non-uniform, but also spacing also non-uniform. So this one you cannot sort of start with analysis. Everything you have to design quickly. So we use actually developed the Gaussian beam modeling. So with that, you can design very quickly, maybe within a week, rather than months and months of simulations. So these are some of the scientific missions. Mars Reconnaissance Orbiter. It's a 3-meter ADE type. It's a dual band. And then Springback Reflector developed by Boeing, and the Galileo Reflector, which was mesh is done by Harris. So the mesh actually didn't deploy for almost 2 years, so they have to take it close to the sun, heat it up, and by the time they brought it, there's no fuel, so that sort of failed a bit, but I think they sort of made it another one. SMAP I have shown, so Voyager mission again is, you can see, uses the frequency selective surface, so some of the technologies. And PIM, I think I mentioned, so basically PIM is very important, so you can see the frequencies when they combine F1 and F2, how the harmonics on the top right, harmonics are coming, so order of the PIM is very important, so that depends on the separation between the two worst case channels, F1 and F2 on the transmit, and how they fall into receive. So order of the PIM is M plus N. So the lower order is very difficult, like third order, fifth order, seventh order, up to seventh order is very difficult. So you have to measure them. So there's no other way. So measurement is very expensive. So you have to take a lot of precautions in the design itself to minimize the PIM. So you can see how the PIM is measured across with the thermal cycling. So the blue curve is the worst case, and then the average PIM is, you can see our spec was 135. You can see we met all the specs, 50 different hot and cold through thermal vacuum. You can see the measurements here. So the antenna feed is enclosed in a thermocool box. And then where you pump in LN2, so to take out the heat and cool it, etc. And then calibration is very important. So it's a painful measurements, but you have to do it. Some antenna test ranges, of course, you need test ranges to measure the antennas. We have 50 by 50 planar near field. We have 12 by 12 planar near field, bistatic range to characterize the frequency selective surface, etc. Spherical near field to measure the omni type antennas or low gain antennas. Compact range reflector to measure some classified systems, 6-foot wide zone, and anechoic chambers to measure the feeds, etc. So I think that's all I have. So I just want to say that antenna field is very challenging to work with. So understand the basics. Not only understand the basics, you apply and what you learn to real hardware. And then when you become slightly more experienced, you develop your concepts yourself out of box ideas. And sometimes you fail, but don't be afraid to fail. But of course, you cannot fail too often. Once or twice is okay, but you can't fail too often. Acquire critical skills, that's very important. A lot of people think that software is the king. No, it's not. Hardware is the king. So you have to know the hardware. And once you know the hardware, see which hardware to use and given the requirements, of course, you start with requirements. So within quickly, maybe a week or two, you can come up with a design. And then, of course, software knowledge is important, but that's not the only thing. So I would say hardware is more important, and the software, you use it when needed to verify your design and get more accurate performance. So mechanical is important. You have to work with mechanical people. Manufacturing, so you have to meet proper tolerances. So manufacturing is also very important. And system knowledge is comes handy because you have to work with system people to understand their limitations, and then you have to translate their requirements to the design of the antenna system. And customer understanding is also important. So there are other things, cost and mass and other things. So you have to see which one is more important. Performance is not the only one that is important. Sometimes cost, mass, I think, plays a major role in the performance. So work with passion. So when you work with passion, of course, you get the results. It makes a big difference. You don't have to work too hard, but work smart. But that all depends on if you're a student, of course, acquire the knowledge. work with your process and learn as much as you can. And also make it a point to read journals or what is published outside. A lot of people don't read, and they don't know what others are doing across the world. Like sometimes Europeans are doing very good work nowadays, and Asians are doing good work too. Sometimes Canadians, etc. Yes, so you have to know what people are doing. So innovation is the key to develop these advanced technologies. So it should be the daily routine of engineers to always think of innovation. So because requirements are changing, it's never same design again. So becoming tighter and tighter. Some other constraints are coming. So sometimes they have to make it cheaper. So this is the hope I'm not upsetting the academic people here. I would say engineers innovate and researchers publish. Of course, engineers also publish, researchers also innovate, but these are the main, if you're an engineer, I think you have to innovate. So this is the quote from, I leave with that quote, innovation distinguishes leaders from followers. This is from Steve Jobs, ex-CEO of Apple. And I just leave with this audio. I want it's self-explanatory. This is the B-2 bomber. Right now we have a contract to develop more advanced than B-2 bomber, B-21. So some design work is going on. So there's a stealthy aircraft. So while the video is playing, maybe you guys
The B-2 Spirit. The B-2 was originally intended to carry nuclear bombs deep into Soviet territory if the Cold War had ever turned hot. Its shape, paired with the plane's stealth systems, would enable it to be undetected by Soviet radars. The B-2's long range meant it could fly deep into enemy territory and return home. With the collapse of the Soviet Union and the end of the Cold War, the B-2 has been used as a conventional bomber. It made its combat debut during the Kosovo War in 1999 and has since flown sorties in Afghanistan, Iraq, and Libya. More recently, the B-2 has been placed in bases in the Pacific as part of a strategy to deal with potential threats from North Korea. Here's why it's one of the most feared aircraft in the world. The B-2 bomber was shown to the public for the first time in 1988, just before the end of the Cold War. Its stealth capabilities were virtually unmatched. The B-2 can carry 16 2,400-pound B-83 nuclear bombs, but its official limit of 40,000 pounds of ordnance means it can carry a massive amount of precision-guided munitions. The B-2 has a max range of 6,900 miles on a single tank, but aerial refueling can keep the bomber up indefinitely. On one bombing mission, two B-2s flew a 34-hour round-trip mission from Missouri to Libya and were refueled in the air 15 times. Each of the current 20 B-2s in service are named after estates. Here, the Spirit of New York can be seen at the British Royal International Air Tattoo in July of 2012. The B-2 is a flying wing aircraft, so it has no fuselage or tail. This means it has low drag, high structural efficiency, and generates more lift than other fixed-wing aircraft. The B-2's max speed is Mach 0.95, or 630 miles per hour.
Okay, I think that's it. Any questions?
Sir, thank you very much, sir, for your exciting and interesting lecture. So really you have shared a lot of works related to industry and definitely for the young engineers, those who are attending this, definitely will open up the eye to work on the industry related problem rather than only stick with the publication. So thank you very much, sir. I think we don't have much time to take up the question, but however, we can take some one or two questions. Before that, I would like to invite Dr. Chinmay Saha to say some few words.
Yeah. Thank you, Professor Kartikan and Nishingho for inviting me on this virtual podium. And sir, congratulations and thank you very much for this excellent talk. I mean, most of the antennas you have talked about is pretty high gain antennas, highly directive, but your talk has been quite omnidirectional, or I can say rather isotropic. You have covered the full horizon of space antennas and the ground antennas, starting from the basics, fundamentals to state-of-the-art thing. And some of the stuff that you have talked on like especially the new bands like the dual band, tri-band, and then you talked about some of the upcoming works. So yeah, I think the candidates and the participants have learned a lot from this thing. I have just a couple of queries also. Like I won't ask technical questions because I mean, you from your published work and from your book, especially the Bible that you have written on the space antennas, all the space antenna researchers and many of my students, colleagues in other ISRO centers, they follow that book with Artec House, right? And also you have that book on electromagnetic engineering. That also is a nice book. So I have one particular query to you, especially for young researchers who are trying to get some problem for pursuing research on space antennas. What is your suggestion from academic perspective? Like whether they should start on the satellite based antennas, maybe some CubeSats or something like that, or do you feel like the ground station based antennas are more appealing? Or I mean, considering the infrastructure that is available in academic institutes, especially from Indian perspective, if you can comment like how to start a problem and how to search a problem, whether they should start with the satellites, CubeSats kind of thing, or to start with the ground station kind of applications. So this is my first query.
Only one?
No, I have few more. Probably we'll we'll go serially.
Okay. Yeah, that's it. So I know the Indian environment is a bit different. I think a lot of people work on microstrip because it's easy to make. And but what I suggest is actually you see what the Indian industries need. For example, ISRO, they use a lot of reflectors, but I don't see any research on reflectors happening. So it's very important field. And then DRDO does a lot of other things too. So radar systems and other things, phased arrays. So I think somehow, of course, you don't expect too much from academic institutions because the students want to graduate and quickly publish some papers, but always it's better to have some industry alliance. So I would say actually it's not up to the universities, but also I encourage all the industries to work with the universities like ISRO and DRDO already doing to a certain extent, but probably that's not enough. So here we have a lot of collaborations with universities. We have several programs like Untitled Prodigy program where we get interns from the university. Every year I have 2 interns, so they work with me, they learn, and as soon as they graduate, we hire them, or they go to other companies. It's government actually pays for us to train these students.
Yeah.
So,
Right.
so something like that should be there. I think I heard that Indian government also has a lot of schemes like that. So I think you have to find out, and unless there is some relevance to applications, so I don't think you get more satisfied during doing pure research is fine. I think we're all engineers, so our title is engineer, so we have to behave like engineers. So we're not like basic researchers doing MS.
Yeah.
So unless there is a relevance to the hardware, I think you can do. I mean, basic research, that's fine. But for engineers, I think unless there is a relevance to practical problems. So it's not just the reflectors. I think reflector is one space, and then the ground antennas. But a lot of these applications like Manpack, I think I'm sure India has also a lot of applications. So I think there is. I would say that there is actually industry-wise also there are not many companies doing this sort of things. So even
Right.
so that's why the DoD wants to develop the industry base within years. So they basically give all the primes like Northrop Grumman to work with small companies like 50 or less. So that they can we can work with them, make them cheaper. I mean, big companies like they're expensive, so they have their own added G&A, and so they want to encourage small companies. At the same time, they want to train them. So I think it's don't just work on microstrip and do something and design and measure and write a paper. So that's okay for graduating, but it doesn't give you confidence that what you learned is you can take it to the industry and work from there. So it's important. I think industries have to support definitely, and then the universities have to work with industries, and the government has to support mostly. I think there are a lot of programs, looks like now.
Yeah. Yeah. Thank you very much, sir. Dr. Kartikan, can I take a couple of more minutes from you? Yeah. Yeah. So, sir, one more thing is like here you talked about so many things, and it really calls for the system engineering. Most of the academic research that happens, like people just work on isolated antennas or rather standalone antennas. But this type of research activities requires basically the system development. So it is not only the antennas, the peripherals, the circuit, I mean, a lot of mechanical stuffs, all these things are involved here. So what happens is sometimes the students get overwhelmed to see the total periphery of the work. So what is your suggestion for the beginners in this particular field?
Beginners, you can start with, of course, you need some help from industry to identify what are the system parameters, and I think they have to work with academic institutions to tell them the problem, not just the antenna, but where the antenna goes and what are the constraints and the physical size, the mass, and other things. Of course, mass, those things may not be that critical when you develop the technology, but they have to give you some advanced technology to work with, like multiple bands or the feed covering multiple bands, or high performance, maybe high efficiency or low cross pole. So there are a lot of still I would say that whatever we developed so far is not even 25%. I would say that next 10 to 20 years, I think new technologies will come, especially with 3D printing and coming up, and how to make them cheaper and how to make them better. So that all needs some system inputs, but I don't expect the academic universities to really develop the system. So it has to come from whatever the sponsors of the program, either industry or government. So
Yeah. Yes, sir. Thank you very much. I think Dr. Kartikan would like to take up some of the questions. That is available in the chat box. If needed,
sir.
I'll chip in again. Yeah, please.
Yeah, definitely. Sir, thank you, Dr. Saha, for joining us. Sir, we don't have much time, so probably one question I can take it from chat box. I request the participants to send the question through email. Sir will clarify you. Sir, actually, what is the role of 3D printing in future antenna technology? You mentioned about 3D printing.
yeah, 3D printing is very important because it's a new technology. Initially, I think most of the 3D printed technology is dielectric based. So the powder, actually, you put the powder in and then you define the shape, and then it prints and it comes up with the unit. But nowadays, a lot of technology is developed to 3D print the metals. So the special alloys developed. There are machines actually developed. I think there's a German machine which is pretty good. So that can actually 3D print the metal. And still, I think still it's initial stage. Still, the tolerances are not there if you want to use that technology for horns or some with high frequencies where your tolerances are important. I think it's not there yet, but so if you have that, then you have to 3D print and then post machine. So it's two processes. So I think we also trying to develop more better 3D printing technology, meeting the tolerances what are needed at high frequencies. So I won't say that it's there yet, but probably I would say 30% it's there. So other thing is qualification, how you, generally when you 3D print with metal, the surface is very rough. So that means your losses are going to be high. So you have to post machine to reduce the losses. So you can do that way, but then again, it's one more process. So the technology being considered is how to 3D print even at terahertz frequencies, meeting the tolerance requirements needed. So it's not there yet. I think it will be probably another couple of years before we see a 3D printed antenna or component which meets the tolerance requirements.
So thank you, sir. Sir, one last question.
Yeah, I have time, so unless you guys have to go.
Okay.
Yeah, you can take probably another 10 minutes, maybe, Dr. Kartikan. Yeah.
Surendra Kumar, yes, sir. Dr. Surendra Kumar Gupta asked, sir, what is the role of radome or substrate used in antennas for satellite communication to overcome effects of high variations in temperature?
Yeah, that's a good question. So there are different types. It's called thermal design. So basically, you can have a thermal cover on the top of the reflector, for example, or a thermal cover on the top of the feed horn. So these are low dielectric constant, and this is material which are available, like germanium coated kapton, typically what we use. So it's a thin layer of germanium coated kapton. So it's probably 1 or 2 mils, not very thick, and very low loss, something like less than 0.02 dB or so. So whereas on the reflectors, since it's a large area, you have to make sure you need to have tensioners, because the shape of these thermal blanket, we call it, so, or MLI. So this has to be RF transparent. But when you have, say, for example, on a 6-foot reflector, so it's sort of loose, so it affects the side lobe. So you need a tensioners to tension the surface and on the top of the reflector. Sometimes people use bare graphite without any thermal cover, because graphite is very thermally, it can very stable. So it all depends on the thermal. So that comes from mechanical group. They have to do thermal analysis and then say that given the altitude of the satellite, or these are the temperature ranges. So depending on, sometimes we can live without any cover. Sometimes we have to use thermal cover to protect it and reduce the thermal excursions within the payload. So it's a very important design as well. That's why we test all these antennas over T-back chamber, where we cycle the temperature from hot to cold to ambient several cycles, maybe around at least minimum 6 cycles. Before that, we have to condition the hardware with the hottest, keep it in the hot, and then pre-cycle it over maybe 5 cycles or so to sort of relieve the tensions on the hardware. So all these thermal designs, I think testing is also important.
Yeah, thank you, sir. The one more question from Kahan from Astrines. What is the success rate of deployable mesh reflector? Is there any statistics regarding the success rate in spaces available with you?
Yeah, I think that's a good question. I think there's some failures before, so maybe that's when the mesh deployable reflectors are in the people started. So that's why the one I show Harris deployment failed for one of the scientific mission program. So Galileo. So right now, I think the technology is very good. Actually, lately I haven't seen any failures. Sometimes actually the deployment boom may not work. Sometimes the mesh may not deploy. So you have to shake it, the spacecraft, to sort of release the mesh. But there are failures on and off. So that's the risk with these technologies. But technology is there. Actually, people are actually developing the deployable mesh at high frequencies at Ka band and even EHF band, 45 gigahertz, with a lot of openings per inch, 40 openings per inch. So currently, Tendak actually deployed a 3-meter mesh reflector for NASA mission, so which was, I think, successful. So they already have deployed 0.5 meters and 1 meter type reflectors for some missions. So technology is there. I think I would say the failure rate is not that not that high. It's actually a success rate is very good on this deployable mesh reflectors. That's the only way to stow in a small volume, especially if you go to small satellites and UAVs, and you cannot have big reflectors because available space is small. So you have to stow in a small volume and deploy the reflectors. I think it's a future technology.
Yes, sir. Thank you, sir. So one more question related to this. With this, we can wind up. What is the fabric material used in deployable mesh?
This is typically gold molybdenum. It's a gold moly component. Actually, it's a gold-plated molybdenum wire because it's high tensile strength and also very low mass. It's something like 0.025 kilograms per meter square of aperture. It's very lightweight, and it can go up to 200 degrees C, and it can on the lower side it can go to minus 160 or so. So thermally very stable. So high tensile strength. So it has all the properties you need, and then low insertion loss. So depending on density of the mesh, you can either 10 openings per inch or 40 openings per inch. It's basically transmission loss, that's all. The insertion loss of the mesh is very low. Technology is there. I think people tried with the Oricon type other material, which is DuPont makes, but it was not that successful. So gold moly became a standard in the industry now.
So thank you very much, sir. So thank you for all the participants who have joined this wonderful lecture. I would like
We see a lot of appreciation in the chat box.
yeah, that's also,
I can't see the chat box though.
Sir can able to see also, so that's why I'm not reading it actually.
Yeah, it's all super appreciation from different students, different researchers. Yeah. So I just want to mention, like, Dr. Rao is a very good human being. He's of course he has immensely contributed in this particular field. We have been really blessed with his association in various forms. He has visited us quite, in fact, my institutes, and he has interacted with our nanosatellite team, some of our students. And the flagship event, that Indian IEEE Space Antenna Workshop that we started in 2018, he has been the speakers for last two versions. Probably this year, because of the pandemic, will go in virtual mode. So Dr. Rao doesn't need anything to say. He's a legend in this particular field, and of course, he's a leader. So with this, I just conclude my part of this thing. Yeah.
No,
Dr.
I'm not the leader. It's in I think I'm still learning.
Yeah, that confirms that you are the leader, because true leader says like that.
Nobody is the leader.
Yeah, definitely it is a great opportunity to host this Sudhakar sir lecture during this pandemic by NIT Trichy MTT chapter. So he readily agreed, and we have made a very wide publicity. Nearly 425 registrant actually registered for this, and everyone is attentive. So thank you very much, sir, for giving me an opportunity to host an NIT Trichy MTT chapter. So with this, we can conclude.
Thank you, Professor Karthikeyan and Professor Nrusingha Pradhan. So thanks for organizing this, and appreciate all the participants. And hopefully, if you have any questions, feel free to contact me. I think
in the chat box, I will provide your mail ID, sir.
Okay.
Maybe they can interact with you.
Okay.
Okay,
Stay
sir.
safe, and hopefully we'll see you in the next INCAP conference.
Definitely, sir.
Yeah.
Actually, unfortunately, we are able to connect it. So next time we will try to meet it.
Okay. Thanks very much. Appreciate it.
Yeah, thank you very much, sir. Thank you.
Yeah, thank you, sir.
one and
Thank you,
all.
Dr. Karthikeyan. Yeah.
Thank you, sir.
Now I